some binary compounds or simple binary compounds across the elements. So simple binary compounds of the elements, they exhibit interesting trends regarding their structure and properties. For instance, hydrogen, oxygen, and halogens, they form compounds with most of the elements. So hydrides, oxides, and halides, they will be revealed here to give like some insight into trends in bonding and properties. So first, let's start talking about the hydrides. So the hydrides of the elements, they can be classified as molecular, saline, or metallic. So hydrogen reacts with most elements to form hydrides that can be molecular, saline, or metallic. And some of them, they cannot be so easily classified, so they are termed intermediate. So we can see here in this table a description of the hydrides that are saline, intermediate, metallic, or molecular with different elements. So we can see the nature of these hydrides with the different elements as depicted in this table. So we can see that metals here form saline compounds, transition metals form molecular, metallic hydrides, while the non-metals form molecular hydrides. And then here, copper and zinc form intermediate species. Regarding the oxides now, oxides are a very important type of compound, and we will study like their properties and applications along this course very much. And so here we just give a brief overview in terms of like some kind of periodicity or periodic properties. So metals form basic oxides and non-metals form acidic oxides. So we will study later in more detail what are the acidic and basic oxides as well. So the elements form normal oxides, peroxides, superoxides, suboxides, and also non-stoichiometric oxides. So many different oxides of the D block elements exist, having a huge variety of structures that vary from ionic compounds or ionic lattices to covalent molecules. And the high reactivity of oxygen and its high electronegativity leads to this, like to a vast number of binary oxygen compounds. And many of these compounds can bring the high oxidation states in the second element, or the group oxidation state in the case of some transition metals. So here, this table, for example, shows examples of oxides for the different elements in the periodic table. And you guys can see like the variety of oxides that can be formed, either like with metals, look at the case of manganese or molybdenum, for example, like several oxides can be exist, but also in the case of nitrogen here, which is a non-metal, we can have like several types of oxides as well. So, as I mentioned, the non-metals form acidic oxides. In this case, the electronegative atom draws in electrons from coordinated molecules, liberating hydrogen plus. So the acidic oxide is actually an oxide when reacts with water, liberates hydrogen plus or hydronium ions in the solution. So we will study this also in our lecture about acids and bases. And also, like the basic oxides is the opposite. They react with water, generating OH minus ion as a result of this reaction. So the acidic nature of the oxide increases as we go left to right across a period and decreases as we go down a group for a given oxidation state. So this kind of follows the trend in electronegativity, which is also related to size, for instance. So acidic nature increases as we move from left to right across a row in the periodic table and decreases as we move down a group. And many oxides are known for D block elements, as I discussed previously. Also, I will discuss the halides of the elements. So halides for the S block elements are predominantly ionic, while the halides for the P block elements are predominantly covalent. In the D block, low oxidation state halides tend to be ionic, and high oxidation state halides tend to be covalent. So also, binary halides of the D block elements span several metals or all metals in most oxidation states. So the D halides are typically ionic solids, while like higher halides then have a covalent character. And here in this table, we show like the different types of halides that can be formed with the different elements in the periodic table, which include the metals and non-metals. So again, for some metals, we can have a huge variety of halide species, halide compounds. So the last concept that I would like to discuss during this lecture, which is very important, refers to the anomalous nature of the first member of each group in the periodic table. So this is very important. So interestingly, the first member of each group in the P block, they show like significant differences in properties relative to the other elements in the same group. And this is assigned to their smaller atomic radius and also lack of low-lying d orbitals. So for the 3D metals, or for the metals in the first period of the transition, or in the first group of the transition, metals in the first period transition metals, they form compounds with lower coordination numbers and oxidation states than the elements in the 4D and 5D periods. So we have a little bit of this tendency in the D block as well. So what's important is the atomic radius enhance some chemical properties of period 2 element is actually also similar to that of the element located to their lower right in the periodic table. And this is referred to as a diagonal relationship. So therefore, let's say this again more clearly. Another important tendency is that the atomic radius and therefore chemical properties of some elements in the first member of their groups, they are similar to that of the element which is located to their lower right in the periodic table. Because if we have an element which is the first element in the group, and then we have an element in the lower right, so we have an increase in size as we go down a group, and a decrease in size as we go from left to right across a period. So the overall result is that the sizes of these two species for some elements is similar, and therefore they have similar properties. So this is why it's called diagonal relationship. So, okay, so let's discuss this again in a more clear way. So, talking about the anomalous nature of the first member of each group. So the chemical properties of the first member of each group in the P block is significantly different from the other members of the group. And this occurs because they have small radius, that is like remarkable, it is significantly smaller relative to the other members of the same group, and its correlated properties such as high ionization energies, higher electronegativities, and low coordination numbers, which occur as a result of this smaller radius. For example, group 14, carbon can form like a huge number of hydrocarbons or catenated hydrocarbons with stronger carbon-carbon bonds. And carbon also can form strong multiple bonds in compounds such as alkanes and alkynes. So this tendency to catenation, to form these chains and ramifications, this is much reduced when we go down the group, for example, to silicon, as a result that the bond enthalpy decreases. So, for instance, for silicon, the longest silane contains only 4 silicon atoms. So, in all these trends that we have discussed so far, we were discussing trends of the elements within the periodic table in terms of vertical trends along, like as we go down or up in the same group, or horizontal trends as we move to the left or right in the same period. However, the element at the head of each group also has diagonal relationship with the element to its lower right. So these diagonal relationships arise because the radius, charge densities, electronegativities, and therefore many of the properties become similar for these kinds of elements because, as I mentioned, we have the effect of going down in a group and going right across the period. So these effects balance themselves, which result in similar properties for the species located in these positions, which is referred to the diagonal relationships. So here we have the numbers for atomic radii, and then here we have the numbers for Pauling electronegativity. So these striking differences between period 2 elements or the anomalous nature of the first element within the group. This is very remarkable in the B block, but this also exists in the D block, but it's less significant or less markedly manifest itself. Like we have that the properties of the D series metal are different from those in the 4D and the 5D series. For instance, the lower oxidation states in simple compounds are more stable in the 3D series, with a stability of higher oxidation states increasing down each group. Also, the degree of covalence and the coordination numbers increase between compounds of the 3D to the 4D and 5D elements. Therefore, with this, we finish our second lecture in periodicity and atomic properties. So wrapping up, in these first 2 lectures, we studied periodic trends and how several properties vary across the periodic table. In this case, we focus on atomic properties such as atomic and ionic radii, ionization energy, electron affinity, electronegativity, polarizability, occurrence, which was discussed based on soft-soft and hard-hard interactions, metallic character, oxidation states. We also discussed some periodic trends or properties regarding compounds. So like we discussed coordination variations and trends in coordination numbers, bond enthalpy trends, and also some binary compounds with hydrogen, oxygen, and chlorine. And then we ended by discussing the anomalous nature of the first member of each group relative to the other members of the group, and diagonal relationships as well that these elements present with elements that are located to their lower right in the periodic table. So thank you very much.